All right. So in this example, again, we're going to see how an ODE arises from applying Newton's second law of motion, F equals ma. Specifically, we will use our model to understand the motion of a pendulum. Let's see what our example is. We want to consider the classic single pendulum problem. So the example says a point mass m is suspended from a fixed pivot by a rigid massless rod of length L. So this is our pivot, and then we have a rigid rod of length L. We are assuming the mass of this rod is negligible compared to the mass of m that we have here. That is how you should read this assumption, massless rod. The mass is negligible compared to the mass m. So we have this pendulum hanging from the ceiling. It's swinging back and forth on this frictionless pivot point that we have on the top. So the pendulum is free to swing in a vertical plane. This is our vertical plane. The pendulum is swinging in this vertical plane under the influence of gravity. The force that we're going to consider is the force due to gravity with no air resistance or other dissipative forces. So in this example, we're going to ignore the impact of air resistance. And this is the dissipative forces. It refers to those forces that reduce the mechanical energy of the system, like friction, like air resistance, like dynamic friction or fluid resistance. So we are ignoring these forces. We're going to focus on the force due to gravity. So what we are interested in is determining the angle theta. So this angle, the angle between the vertical and the rod, the angle between the vertical and the rod, which is a function of time, theta of t, the angle theta of t, which measures the deviation of the rod from the vertical. Vertical means perpendicular to the ground. As a function of time. So the main goal here is to come up with an equation our goal will be deriving the equation, the differential equation that this angle theta of t must obey, the equation that governs the angle theta of t that the rod makes with the vertical. That is our goal. So let me quickly go over the assumptions for this model. Some of them we went over, but I want to just emphasize on them. So assumptions for this model, the mass of the rod is negligible compared to the point mass m, as we discussed. In a sense, we are assuming that the rod is massless. The motion takes place entirely in a plane with no lateral or three-dimensional movements. So we are assuming that the motion of this pendulum is inside this vertical plane. We're not going to consider the motion outside of the plane, coming out of the plane or going inside the plane in the third dimension. The rod remains perfectly rigid. The rod will have a constant length L. The length of the rod will not change. Okay. The gravity is constant and acts uniformly downward with an acceleration g. So here in this problem, the force due to gravity, it will be applied to the mass m, but it will be equal to mg. We will not the variation of the force with the distance from the center of the earth are like negligible compared in this particular problem, as opposed to one of the previous problems that we solved, that we actually considered the variations of the force due to gravity with the distance from the center of the earth, because here the vertical displacement is very small, so those variations will not play a key role. We're going to assume that the force due to gravity is constant. It is equal to mg. It acts downward. Okay. And there are no external forces acting on the system. So the only external force that acts on this pendulum is the system that we're considering is mg. On the mass m, we will have the force due to gravity, as I will discuss very soon. That is the external force applied to the mass m. And also we will have this force due to the tension in the rod. That is another force that is applied to the mass m. That's like an internal force that is applied to the mass These are the forces, as we will discuss, that we should consider when we want to consider the motion of the mass m. All right. So far so good. Now let's start solving our problem. We want to apply the Newton's second law to come up with the equation of motion. And to do that, as you all know very well at this point, is that we need to set up a coordinate system, give a name to the quantities of interest, and then draw a free body diagram, and then apply the Newton's second law, F equals ma. So let me draw our pendulum again. So we have our ceiling, we have this frictionless pivot, and then we have this rod of length L, and we have the mass M, the point mass M is here, and then the angle theta, remember the angle theta is the angle with the vertical. All right, so let me again be very clear about what the goal is here. Our goal in this problem is to derive a differential equation governing theta of t, a differential equation that theta of t must satisfy based on Newton's second law. Newton's second law. We will use the Newton's second law to derive this differential equation. As you will see in this example, I'm not going to solve the differential equation. I will make some comments about the differential equation, but we will not actually do the solution part in this example. All right, one more comment that I want to make before the setting up my coordinate system and then drawing the free body diagram. The other comment that I want to make is about a certain convention for measuring the angle theta. So what I'm going to do in measuring the angle theta, I'm going to assume that theta here is varying from negative pi over 2 to pi over 2. Negative pi over 2 would be here. 0 would be here, pi over 2 will be there. So that is the convention that I'm making for the angle theta. And positive, theta is positive, is if the rod is to the right of the vertical. Theta, in my convention, theta is negative if theta is to the left of the vertical. So let me actually write this down as well, and then I will set up my coordinate system and draw the free body diagram. So we assume, let me also write this, we assume theta of t is between negative pi over 2 to pi over 2. So I'm gonna now assume that the variation of this angle is from negative pi over 2 to pi over 2, instead of assuming it's going from 0 to pi. That would have been another way to model this problem, but the way I'm measuring theta, when the rod is vertically aligned, theta is 0. At this point, theta is equal to pi over 2. In my measurement, at this point, theta is negative pi over 2. So this is not the only choice, but it's one of the choices that we could have made for measuring the angle theta. And also, we adopt the convention that theta of t is greater than 0 when the rod is to the right of the perpendicular, is to the right of the perpendicular, and theta of t is negative when the rod is to the left of the perpendicular. So these are our conventions. You may choose other conventions and then solve the problems with those conventions. In my solution, I'm gonna make these conventions. Okay. Now, and let me set up my coordinate system and introduce the symbols that I'm going to use for different quantities of interest, and then I will draw a free body diagram. This is always the procedure for me when I want to apply the Newton's second law. So I'm gonna consider this pivot point as the origin, and then I'm gonna choose this horizontal as my x-axis, the vertical as the y-axis. And of course, according to our assumption, the motion is happening in this plane. So I don't even need to consider the third dimension, but it doesn't hurt. So this z-axis is coming out of the plane. Of course, there's nothing happening in the direction of z, as we discussed when we were going over the assumptions for this model. However, I just drew the z-axis. It doesn't hurt. It doesn't hurt if we have the draw the z-axis as well. But everything here is happening in the xy plane. This z is coming out of the plane, and nothing is happening in the direction of z. All right. So far so good. And now I'm gonna introduce the notation for position. So I'm gonna denote the position vector as usual. I think I always denote it by r of t, the position. And r of t, here the position vector is the vector that connects the origin of my coordinate system to the position of this mass m. That vector is the position vector. The body of interest here is the mass m for me, and then the position vector will be obviously x of t times I plus y of t times j plus 0 times k. There is nothing happening in the z direction. Remember, I is the unit vector in the x direction, j is the unit vector in the y direction. So let me actually, just as a reminder for everyone, I is 1, 0, 0. J is 0, 1, 0. K will be 0, 0, 1. Of course, nothing happening in that direction. So we have 0 K. I didn't write it. So the position of this mass at any time, it has an x coordinate and a y coordinate. These are the x coordinate and the y coordinate of the mass m. Now, since ultimately I'm interested in theta, it would be a great thing if I could write this x and y in terms of theta, and that's actually very easy to do. Look at this triangle here. Let me use a different color. This triangle here. So this is your x coordinate, and in this right triangle, we will see that the x coordinate of the mass is exactly L sine theta. And of course, theta is a function of time itself. The y coordinate of the mass, the length of this segment is L cosine theta. However, since it is in the negative y direction, the y coordinate will be negative L cosine theta. So here, this is our formula for r of t with x of t equals L sine theta of t, and y of t is equal to negative L cosine theta of t. And I want you to all notice that this agrees the way we set up the coordinate system and the convention we had for the sine of theta, they are consistent with each other. This is something that I want you to check in private. This is consistent with our convention for the sine of theta, because notice that if theta is greater than 0, and of course theta is always between negative pi over 2 and pi over 2, so greater than 0 means that it is between 0 and pi over 2, then sine theta will be greater than 0, and that means that x is greater than 0, which is completely consistent with the situation that we have here. Yes, if the mass is to the right of the perpendicular, the x coordinate is positive. And also, if theta is less than 0, and again, remember that the theta is always between negative pi over 2 and pi over 2. So when we say theta less than 0, that means that theta is between negative pi over 2 and 0. When sine theta is less than 0, and then that means that x coordinate will be less than 0, which is again in agreement with this, with everything that we have here. when the rod is to the left of the vertical, the x coordinate is negative. The x coordinate will be negative. All right. And cosine of theta of t is always a positive number, that when theta is between negative pi over 2 and pi over 2. So y of t in this formula that you see here is always a negative number, which again is consistent with what we have here. As the pendulum is swinging back and forth, the y coordinate, because of the way I chose my coordinate system, is always a negative number. So everything is perfectly consistent. Nothing weird is happening here. We did our analysis. We made sure that everything is careful and consistent. So that is the position vector for our mass, the position vector of the mass m, the position vector of the mass m in our coordinate system of the mass m. And then what will be the velocity vector, the derivative of the position vector? This is dr dt, which will be equal to x prime of t I plus y prime of t j. And then what will be the acceleration vector? The acceleration vector, that is the derivative of the velocity vector with respect to time, which will be x double prime of t I plus y double prime of t j. Now, if you like, you can call this, you can call the first component of v, you can call it vx, the x component of the velocity. You can call this Vy, the y component of the velocity. The first component of the acceleration, you can call it Ax of t. The second component of acceleration, you can call it Ay of t. All right. So far so good. I introduced the symbols that I'm using for the position vector of the mass m, the velocity vector of the mass m, the acceleration vector of the mass m. Eventually, I want to write the Newton's second law for the motion of this mass m. And also I noticed that x of t and y of t, they can be expressed in terms of theta. That is very important for me because ultimately I want to have an equation for theta. So far so good. Now let me draw the free body diagram. Now that I set up my coordinate system, I gave a name to the quantities of interest, the quantities that I need in order to understand the Newton's second law. Now I'm gonna draw the free body diagram. So this is the mass m, and one of the forces that is applied to this mass m is the force due to gravity, the external force that is applied to the mass m, force due to gravity, and of course, the internal force that is applied to the mass m is the force due to the tension of the rod. It will be in the direction of the rod. We don't know its value at this point, but it is exerting a point to this a force to this point mass. So this is in the direction of the rod. Ft, I'm gonna call this tension force F subscript T, force due to the tension in the rod. So this is where the rod is. The rod is here. And then of course the angle with the vertical is theta. This theta is changing with time. That is the angle with the vertical. Okay. So far so good. Now let me give you more information about this Ft and Fg, and then we will write the Newton's second law. We have, so first starting with Fg, what is this Fg? We know that we assume that the magnitude of the gravitational force is not changing, it's uniform. And we know that the magnitude is mg. And what is the direction here? It is the direction is negative y-axis. So we have the unit vector negative j. This is equal to negative mgj. J is the unit vector in the positive y-axis direction. Negative j is the unit vector in the negative y-axis direction. Okay. And then what about this Ft? It would be great if I could decompose this into its horizontal component and the vertical component. So this Ft has a horizontal component and a vertical component. So what will be the magnitude of the horizontal vertical component? This is theta, so this guy is also theta. The magnitude of the vertical component will be the magnitude of ft times cosine theta. Using a little bit of trigonometry, we will see that the magnitude of the horizontal component will be the magnitude of ft times sine theta. So now using the triangles that we see in this picture, so f subscript t is equal to the horizontal component, as you can see, is it points in the negative, it points in the negative x direction when theta is positive. So it will be negative magnitude of f of t, the size of f of t, times sine theta I. It is in the direction of negative I when theta is positive. And then this formula, you can easily check that it also works for the case when theta is negative. When theta is negative, sine theta will be negative. Then we have negative sine. Also, the whole thing will be positive, which agrees with the fact that in that case, the horizontal component points rightward. And then the vertical component is the magnitude of the tension force times cosine theta times j. It is pointing upward in the positive y direction. Please notice that at this point, we do not know what this quantity is. The size of this tension force in general can depend on time, and we do not know what it is. Keep that in mind. This changes with time, and we do not know what it is. All right. So this is what we have for our forces. I just decomposed the tension force into two components, the horizontal component and the vertical component. Please, in private, check that, convince yourself that this formula that I wrote also holds if the mass m is to the left of the perpendicular, it's to the left of the vertical line. The same thing will work. Or because the picture I drew, the way I drew it, the mass m is to the right of the vertical. But the same thing will work if the mass m is to the left of the vertical because of the convention we had for theta. All right, so far so good. Now let's apply the Newton's second law. We have our free body diagram. We have everything that we need. We can apply the Newton's second law. By the Newton's second law, we have the total force, which is applied to the mass m, Fg plus Ft, is equal to m times the acceleration of the mass m. So what does that tell me? Fg is negative mgj. J, the unit vector in the positive y direction. Ft, which we just figured out what it is. It's the negative magnitude of Ft. Of course, at this point, the magnitude of Ft is unknown, times sine theta I plus magnitude of Ft. I'm using these vertical bars. When I put a vector inside vertical bars, that means magnitude of that vector. Cosine theta j. So far, so good. So this is Fg plus Ft. And then on the right-hand side, I have Ma, which is MAXT I plus MAYT Remember, let me scroll up a little bit. This is here we go. This is the acceleration, AXTI, AYTJ. Of course, AX is X double prime, AYT is Y double prime. Very soon I'm gonna use that. So what does this tell us? So the I component on the left must be the same as the I component on the right, obviously. And then the J components must also equal. So from this, the conclusion is that negative size of Ft sine theta must be equal to MAXT and negative mg plus size of Ft cosine theta must be equal to MAYT. Awesome. So if we divide by M, we will get AX, the X component of the acceleration vector A, acceleration of the mass M, must be equal to negative the size of Ft sine theta over M. And then the Y component of the acceleration must equal negative G plus size of the magnitude of the vector Ft cosine theta over M. So far, so good. And of course, A is the second derivative of the X with respect to time. AX, AY is the second derivative of Y with respect to time. So now we have these differential equations in a sense. X double prime T is equal to negative the size of the vector Ft sine theta over M. Y double prime T is equal to negative G plus Ft cosine theta over M. And of course, remember, ultimately, I want to have an equation for theta, right? So here, the theta of T is the unknown, the Ft, the tension vector is in the rod is the unknown, X of T, Y of T, they are all unknowns. But I can, as a matter of fact, write X of T and Y of T in terms of theta. We discussed this previously. Let me scroll up. Remind everyone where we did that. Here we go. Here we go. Here we have it. Here we have it. Very good. Let me call this 1. So it follows from 1 that from 1, we have X of T is equal to L sine theta of T, the sine of theta of T. So that tells me that X prime of T is equal to L. Now I have to use the chain rule to take the derivative of sine of theta of T. The derivative of the outer function evaluated at the inner function times the derivative of the inner function. I'm going to write the derivative of the inner function and then the derivative of the outer function evaluated at the inner function. That is what we did here. And now we can take the second derivative. So I'm gonna, L is a constant. I have to take the derivative of this product. So it will be L times derivative of the first term, theta double prime, times the second term, and then plus the derivative of the first term times the derivative of the second term. So derivative of the inner function is theta prime, and the derivative of the outer function evaluated at the inner function is negative sine theta. So this is equal to L theta double prime cosine theta minus theta prime squared times sine theta. That is X double prime of T. Similarly, we can find Y double prime of T. Y of T is negative L cosine theta. Theta is a function of T. So Y prime of T, again, using the chain rule, derivative, L is a constant number. Derivative of the inner function is theta prime. Derivative of cosine is negative sine. So this will be L theta prime sine theta, because the derivative of cosine is negative sine, and also we had a negative here. Those negatives, they cancel each other out. And so I can easily compute the second derivative now. The second derivative, I'm going to keep the L, which is a constant. And now I have to take the derivative of theta prime sine t using the product rule. This is equal to L, derivative of the first term, times the second term, plus first term times the derivative of the second term, derivative of the inner function, derivative of the outer function evaluated at the inner function. So this is equal to L theta double prime sine theta plus theta prime squared cosine theta. All right, awesome. So putting these together, let me summarize what we have discovered. Therefore, so I'm gonna let me give these guys names. I'm gonna call this 2, and then the formula for x double prime 3, the formula for y double prime 4. So now putting 2, 3, and 4 together, 2, 3, and 4, what they will tell us is as follows. So let me scroll up. 2 on the left-hand side, I have x double prime in the first equation. And here I have a formula for x double prime. So I'm gonna use my formula L theta double prime cosine theta minus theta prime squared sine theta. This is x double prime t. This is equal to negative magnitude of f of t sine theta over m. And now for the second equation in 2, I'm sorry, this is 2. For the second equation in 2, where what we had was y double prime on the left. So L theta double prime sine theta plus theta prime squared cosine theta. This is our y double prime of t. And this is equal to, from 2, we have negative g plus magnitude of f of ft, the tension force, cosine theta divided by m. Beautiful. Now we have 2 equations, and these are like 2 differential equations. The unknowns here, one of them is theta of t. Still, we do not know the magnitude of f of t. It is in general a function of time. So still, we don't have one equation for theta. We have 2 equations, and we have 2 unknowns. Theta of t and the magnitude of the tension force. So it would be great if we could somehow eliminate the magnitude of the tension force between these 2 equations to come up with one equation for theta of t. So let me actually be very clear about this. Here the unknowns are theta of t and magnitude of the tension force, which is in general a function of time. And our goal is to somehow eliminate this f of t between these 2 equations to come up with one equation for theta of t. So to obtain an equation for theta of t, we need to get rid of the magnitude of the tension force. And that there are multiple ways to do this. I'm going to tell you one way one thing that you can do to eliminate this magnitude of f of t. So what I'm going to do, my friends, look at the right-hand sides. I'm going to multiply the first equation by cosine theta. I will multiply the second equation by sine theta. If I multiply the first equation by cosine theta, the second equation by sine theta, and then add them up, this term that consists of magnitude of the tension force will disappear. So I'm going to do the following. Let me call this 1 and call that 2. Multiply 1 by cosine theta, multiply 2 by sine theta, and then add the 2 equations. If you do that, these terms that involve the magnitude of the tension force, they will cancel each other out. What will happen to this left-hand side? If I do that, what will happen to the left-hand side? Let me actually write this out. So I'm gonna multiply the first equation by cosine theta. So I will have on the left, I will have L theta double prime cosine squared theta minus theta prime squared sine theta cosine theta equals negative Ft, the tension force, sine theta cosine theta over m. And oh no, I'm gonna multiply the second equation by sine theta. I will get L theta double prime sine squared theta plus theta prime squared cosine theta sine theta. I'm multiplying this equation 2 by sine theta. It is equal to negative G sine theta plus the magnitude of the tension force cosine theta sine theta divided by m. And now we will add these two together. When you add these two together, you will get L theta double prime cosine squared theta plus sine squared theta. This term and that term will cancel out. This term and that term will cancel out. On the right, you will have negative G sine theta. And of course, everyone here knows that cosine squared plus sine squared is 1. So our final equation is, for theta, is L theta double prime is equal to negative G sine theta. That is our differential equation. The differential equation for theta of t, for the angle with the vertical, is theta, can be written as theta double prime t is negative G over L sine of theta of t. This is a second order ODE. It is nonlinear because we have sine of theta. This is highly nonlinear. This is a nonlinear second order ODE. We don't have a method for finding the exact solution. So I'm not going to solve this equation at this point. This is the equation that governs the angle theta of the. This is a second nonlinear second order equation. Folks, let me make one last comment here. Note, if theta of t is small, is very close, is close to zero, then sine of theta of t is approximately equal to theta of t. This is like based on Taylor expansion. If you know the Taylor expansion of sine, when theta is very small, the sine of theta of t is approximately equal to theta of t. Then we can approximate our ODE, we can approximate our nonlinear, we can approximate our nonlinear equation, with the following linear equation, which is theta double prime is equal to negative G over L, which is a constant, times theta. And this is a second order linear equation for which we have a standard solution technique to solve second order linear equation. For theta small, we can approximate that nonlinear governing ODE with this linear ODE, and this one we can easily solve, find the exact solutions. Second order linear ODE. Excellent.